This episode is brought to you by Cisco Educational Premium. For ages, it has been said that mathematics is the mother of all sciences. All the concepts of science stem from mathematics. This alma mater, the nourishing mother, mathematics is truly astounding. And what better concept to demonstrate this than the birth of light as a consequence of solving Maxwell's equations? Maxwell's equations are 4 in number. The first is the Gauss law for electricity, which relates the net electric flux to the net enclosed charge. The second is the Gauss law for magnetism, which relates net magnetic flux to the net enclosed charge. The third is the Faraday's law, which relates induced electric field to the changing magnetic flux. And the last but not the least is the Ampere-Maxwell law, which relates induced magnetic field to the changing electric flux and to the current. But wait, Caleb. What they call Maxwell's equation again? That's a story for another day. Now, the real deal. This is a math show. We're not going to just make sense of statements, but crucially piece together reality from numbers, from mathematics. No shortcuts. These are Maxwell's equations in their differential form. In a vacuum, when there are no electric charges and currents, our Maxwell's equations will evolve to as shown. Our equations are now simpler. The first and the second equations are the divergence of electric and magnetic fields. These two are telling us that if there are no charges present to create magnetic and electric field lines or terminate them, there will be no divergence. The fields will be continuous. They will not start or end. Astonishingly, Maxwell's equations, even in completely empty space, can define and allow the existence of magnetic and electric fields. The other two equations deals with how these continuous electric and magnetic fields behave. The third tells us that the electric field can be created by firings of magnetic fields in the vicinity. Same as the third, the fourth equation tells us that we can get some magnetic fields in the vicinity by firings of magnetic fields. Both of these fields must be at right angles to one another for one of these fields to generate the other. Say in the third equation as shown, remember mathematically, the left hand side of this equation, del cross E, we are taking the curl of this. We are taking the cross product. Any factors within the cross product will always be completely at right angles to the resultant factors, which in our case is the magnetic field. So if the electric field points anywhere in the xy plane, the magnetic fields must be at right angles to it. The same thing goes for the fourth equation. Any change in the electric field causes new magnetic field at right angle to the electric field. Remember, we are solving Maxwell's equations. Now I want to find electric and magnetic fields formulas, so that when we substitute the left hand side, it will match the right hand side of these equations. We want the third and second equations. Remember, we can't get information about electric field without knowing the value of the magnetic field, and we can't get any information about the magnetic field if we do not know the value of the electric field. So what gives? These equations seem to be conjoined and tangled, so to speak. In math talk, we can say that it is a first order coupled differential equation. What we want to do is to decouple these equations so that they will be completely separate equations. A separate equation for E and a completely separate equation for B. Decoupling them, so to speak. Now, let us start with the fourth equation. Let us take the curl of both sides of this equation, and so we get a shown. On the left side, let us use the factor identity, so we get a shown. On the right hand side, let us exchange the order of the derivatives. Now replacing del cross E using the third Maxwell's law, we get a shown. Now combining everything, if you didn't notice, we have successfully decoupled the two equations into a second order linear partial differential equation. Just to review, the left hand side is the Laplacian operator, del square B, which is a factor 2, same as the right hand side, ignoring mu naught and epsilon naught. We have a shown. And so since both sides are factor quantities, the x component of the left hand side must match that on the right hand side. The y components must match too. Same goes for z. Just to remember, we are now finding the solutions to the second order decoupled differential equation. As we had seen, these really three separate equations. One for x, one for y, and one for z. Now we are going to try some functions on how they will solve our equations. Not that we are trying trial solutions for the x component, which is just the same for the y component, and so for the z component. Now I want to look for a function f that might obey the equation as shown, with alpha just a constant. Say partial sub t square f was just proportional to the original f, and similarly for partial x square f, we want to look for a function whose second derivative is equivalent to the original function apart from e to the x, so to say. Can you remember any? Yes, any cosine or sine function fit here. Partial t square cos t is equivalent to negative cos t. We are going to allow for f to have both an amplitude and frequency. F is equivalent to a cos omega t, where we have omega to be the angular frequency in radians per second. So if we have partial x square bx to be as shown, and if both partial x square bx and partial t square bx are proportional to bx, then we are on the right track. We know that partial x square a cos omega t is equivalent to 0. So we need to add some spatial dependence, some x, so to speak. We are going to propose an ansatz, a trial solution, so to speak. For those who took differential equations classes, I know this word, ansatz, went on top of our heads. It's just an example solution, a trial solution. The product of a function that depends only on space times a different function that depends only on time. Looks like the good old chain rule is in our favor. If partial x square fx is proportional to fx and partial t square gt is proportional to gt, that is, they are sine and cosines, then we have partial x square bx as shown. Also, partial t square bx as shown. And so we see that partial x square bx is proportional to partial t square bx, which is exactly what we need. Now let us consider these two functions, our separable solutions. F is the frequency that is waves per seconds. K is the number of waves per meter. You can think of Kx as the spatial frequency analogous to Ft, which is the time frequency. Now calculating the derivatives of our two functions. we have partial x square fx and partial t square gt as shown. And so if our magnetic field is expressed as bxxt as shown, provided by our answers, then we have partial x square bx and partial t square bx as shown. But let's just check. Our guess bxxt is as shown with partial x square bx to be as shown. So it's okay. And so now we need to ask ourselves, does this obey the second order linear partial differential equation resulting from Maxwell's equations? Is partial x square bx as shown? Now replacing partial x square bx and partial t square bx with the expressions as shown, but the left must match the right. So cancelling terms, we get as shown. And so the question we need to ask, does our ratio match the actual numbers of mu naught epsilon naught and the units? Then those are the exact functions that are gonna solve Maxwell's equations. Now let us just look at the units of the ratio f on k as shown. This means that our f on k represents a velocity. Isn't it incredible? And so letting f on k be equivalent to v, then our equation will be satisfied when f on k square is equivalent to v square, which is equivalent to 1 on mu naught epsilon naught. Then what is the exact value of v? We know that mu naught is the permeability of free space, a magnetic constant, and it has a defined value. And epsilon naught is a dielectric permittivity of free space, and it too has a determined value. And so we are able to find the value of v, and we find it to be 2.998 times 10 raised to 8 meters per second, which is what? Which is the speed of light. This is the solution to the Maxwell's equations. The speed of light is the solution to the Maxwell's equations. The only solutions to Maxwell's equations have the property that they propagate at the speed of light, which are combination of magnetic fields and electric fields orthogonal to one another, carrying with them energy at that specific velocity, which is the speed of light or any electromagnetic radiation specifically. It is not only light that travels at that speed, all electromagnetic radiation specifically. And so James Clerk Maxwell created light, at least mathematically. Whether this was just a coincidence or a deliberate attempt, it doesn't matter. What matters is that it is correct. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.